Hi, welcome back. In this video we're going to talk about polar equations for lines and circles. So just like you know what the equation for a line is in Cartesian coordinates, you should know what the polar equation for a line is in polar coordinates. Similarly for circles, you know the equation for circles in Cartesian coordinates. You need to know the equation for circles in polar coordinates. So I've copied down the key exchanges between polar and Cartesian coordinates here. And so let's look at two especially special cases. We've got a line through the origin, and we have a circle centered at the origin. All right, so a line through the origin. Right, we know the equation for a line through the origin. Looks like y equals mx. There's the b, and mx plus b is 0 because it goes through the origin. And for this equation, if we think about trying to take this equation and convert it into an equation in terms of thetas and r's, well, we see this equation here, tangent of theta is equal to y over x. If I divide by x, I get y over x is equal to m. And so what we have is we have an equation which is tangent of theta is equal to m. So if we were to take the arctangent of both sides, we'd have an equation that looked like c theta is equal to some constant. And if we're looking at this line, that should make sense, because what's true about every point on this line? It's that they all have the same angle as if you look at the angle compared to the positive x-axis. Everything on this line is therefore has theta as its theta component of its polar coordinates. So a line through the origin corresponds to theta is equal to some constant. We can even calculate that constant, right? We can take the arctangent. C is equal to the arctangent of m. So if you're given y equals mx, you can figure out that c theta is equal to some constant arctangent of m. All right, the next thing is a circle centered at the origin. All right, so circle centered at the origin. That's an approximate circle. So if we have something that looks like a circle that's centered at the origin, we know that that is x squared plus y squared is equal to some constant squared. Right? That's our equation in Cartesian coordinates. And now we use our other equation for r squared is equal to x squared plus y squared. And what we're seeing here is that this is an equation where we just have r is equal to some constant. And that makes sense. Every point on this circle is the same distance from the origin. And so in polar coordinates, its r component would be the same each time. That would be equal to that constant. All right, and so what this gives us is this gives us some nice regions, some regions in the plane that are really nice to represent using polar equations. So this leads to the idea of a polar rectangle, which is a region in the plane of the form r is between r0 and r1, and theta is between theta naught and theta 1. So what we're saying is that we like regular Cartesian rectangles because this is x is between a and b, and y is between c and d. But when we use equations where we're using r and theta, the shape is different. Right? So when we're talking about r being between r naught and r1, what that is doing is it's giving us an annulus. This is called an annulus. Whereas when we're dealing with theta between theta naught and then theta 1, this is theta 1, then what we have now is we have a cone. And so when you put those two things together, and we are, I wish I hadn't drawn in this circular part here because there really isn't a circular part, it's just the angle. That's the way I have been denoting the angle. What we really have is we have this big, like Pac-Man-like region that's infinite. It's going off into as big as possible. If we put those two things together, if we take both r naught, r is between r naught and r1, and theta is between theta naught and theta 1, then what we get is we get a partial annulus. Right? Because we want all points that are both between r naught and r1, which means they lie in the annulus, but we want the points also between theta 1 and theta naught and theta 1, which are points that lie in this cone region. So this is a region. It's definitely not a rectangle. But this is called a polar rectangle. And that is a region that, when you see a region like this, that's telling you use polar coordinates instead of Cartesian coordinates. We don't have a nice way to write this in terms of Cartesian coordinates, but we do have a nice way to write it in terms of polar coordinates. So let's just do two examples where I'm going to give you a polar rectangle, and your goal is to write it down in terms of the coordinates. What's the lower bound on r, the upper bound on r? What's the lower bound on theta? What's the upper bound on theta? All right, so first example is this region. All right, I'm going to put this is 1. This is the point 0, 1. Oh, sorry, 1, 0. And this is the point 3, 0. All right, so think about it for a second. Pause the video if necessary. All right, so what we're going to do is we're going to think about the radius here. The radius starts at r equals 1, goes up to r equals 3. So this is r is between 1 and 3. And then we have to think about theta. So theta starts out here at 0 and goes up to pi over 2. So this region right here is how you would write this region in the plane as a polar rectangle. All right, here's one more example. Let's talk about a piece of pizza. Right, I'm going to put some pepperoni on it. But it's a piece of pizza that has radius where this point is root 2, root 2, or negative root 2, negative root 2. What is the polar rectangle here? Well, the polar rectangle is, we have the angle, this is pi plus pi over 4, pizza pi, and so theta goes between 5 pi over 4 and then 6 pi over 4, which is 3 pi over 2. And then to figure out what the radius is, we take x squared plus y squared, and we take the square root. So square root of 2 plus squared is 2, plus the square root of 2 squared is also 2. So 2 plus 2 is 4. So r goes everywhere from 0 up to 2. And so this is a way to represent that slice of pizza by some polar coordinates. All right, so let's stop there, and we'll do some more complicated equations shortly. See you soon.